Hello pre-calculus students, and welcome to the second video in our set on taking the derivative of a power function. And I just want to compare what we did before here. We took a special case of ax to the fourth, and we took the derivative and we found that it's equal to 4ax to the third. Okay. Now I want to generalize this process and say, what if I had an equation ax to the nth power? Okay, where n is an integer. Okay. Now let's take the derivative of this. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all of it divided by h, which is in our particular example is equal to the limit as h approaches 0 of a x plus h to the nth minus ax to the nth, all of it over h. And what I want to do here is factor out a, just like I did last time. Okay, so we're going to kind of use these two to emulate it. This is with x to the fourth. We factor out an a. We're going to do the exact same thing here. So this is equal to the limit as h approaches 0, taking an a out of it this time, times x plus h to the nth minus minus x to the nth, all divided by h. And now we're going to apply the binomial theorem. So this is equal to the limit as h approaches 0 of a times, and this is where it gets tricky. It's easier to do this when you have a specific number like 4. Okay, it's a little bit trickier when we have to deal with a non-number like n, a variable, but I assure you it can still be done. So this, remember, this is just n choose 0, and actually I'm going to use a different color here so that you can see it. This is the part that I'm dealing with here. This is n choose 0, x to the nth, h to the 0th. So compare that to what we did last time. Okay, in our particular example, n is equal to 4. So here you see this, instead of saying 4 choose 0 in this step here, we're just saying n choose 0. Instead of saying 4 choose 1, we're going to say n choose 1. So plus n choose 1, x to the n minus 1, h to the first. So basically at each one of the iterations, I'm going to have n choose 0, n choose 1, n choose 2, and then all of the exponents for x is going to decrease. It starts out at 1, it's now n minus 1. Next step is going to be n minus 2, and then all the exponents for h is going to increase. So this is this is supposed to be a 2 here. It's a terrible handwriting there. And I'm going to continue this for some period of time, depending on how big the n variable is. In the case of 4 here, we only have a few steps here, and we eventually stopped at the end here when we got x to the 0th, h to the 4th. So in this case, we're going to stop at n choose n, x to the 0th, h to the nth. Okay. So this is going to continue on for a while, but it's gotta end here at n choose n, and it's got to go, x is now has been decreased all the way down to 0. H started out at 0 and increased until n. And then finally we still have this thing left here, minus x to the nth. Okay. Well, and all of that over h. Okay. And now this is tricky. This is messy. This is hard work. But I assure you it's also very rewarding, both in terms of doing well on a test and also in terms of just understanding and making sense of some very difficult mathematics. So this is all over h. Now let me point out a few things here. N choose 0 is 1. Anything choose 0 is 1. So that's 1. Anything to the 0th power is also 1. So that's x to the n. N choose 1 is always n. I want to highlight this point here. N choose 1 is always n. Okay? And then we have x to the n minus 1, h to the first. So n choose 1 is always n. And that's about as far as I know. All these ones, I don't know what n choose 2 is. I don't know what n choose 3 is because I don't know what n is equal to. So I'm just going to keep writing the same thing. X to the n minus 2 h squared plus dot 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 plus. Now n choose n is also 1. Okay. This right here, this is also 1. X to the 0th is also 1. And so all I have left here is just h to the nth. And then minus x to the n. And as always, the fun part happens when things start to cancel. So you see this x to the n and negative x to the n. That's gone. That's gone. And just like what we did before, we are going to factor out an h. See up here? And make this note here is a big deal because we know that every single one of these terms has an h in it. Okay? And it seems so like unnecessary and silly and superfluous when we're talking about x to the 4th, and of course everything has an h. I can see it. Okay? But here, even though we don't know how big this n is, even though we don't know how long this goes for, one thing that we're absolutely certain is that we started out with h to the 1st, h to the 2nd, h to the 3rd, all the way to h to the n. So whatever terms are in here, and again, I don't know what terms are in, what exactly all those numbers are, but I know that all of these terms have h in it. Gosh, I wish this marker was better. Okay, all of those terms that are in here has h in them. So that allows me to factor it out. So now I get equals limit as h approaches 0 of a times, and I know this first term only has one. Okay, so I can factor out an h. Whoops, that's a little too big. All of this is over h. And again, this first term has only one h in it, so what's left of it is n x to the n minus 1. This second term here is n choose 2, x to the n minus 2. Instead of h to the second, it's now h to the first. And then every single one of these terms has an h in it. And then the last term, it's h to the n minus 1. So now this h is gone, that h is gone, they cancel. And now we can do direct substitution. Okay. And here's the beauty of this comment here. Okay? And it's more than just a comment, it's a fact. Every single one of these terms have an h in it. Every single one of them. So when I take 0 and I plug it in, so I take 0 and I plug it in here, this entire term becomes 0. Every single one of these terms in here becomes 0, and this term becomes 0. Okay? The only term that's non-zero is the first one, because that only had one h in it, and I already factored it out. So all terms have an h in it, therefore, with direct substitution here, all terms are 0 if h is 0. H is 0, every single one of these terms also have to be 0. So everything here reduces down to so all of this stuff here, that's all 0 now. And now all we have left is a n x to the n minus 1. And that is the derivative of f prime of x. I'll rewrite it another way. We'll say f prime of x is equal to n a x to the n minus 1. Okay. And this is a terrific little result here. I wish I thought of this originally, but I'll show you some applications of this. So let's say I had a function, f of x equals 17x to the 5th. Well, this is simple now. This is a. So f prime of x is equal to n, which in this, so a is 17 and n is 5. So this is 5 times 17 times x to the n minus 1, so x to the 4th. So this is 85 x to the 4th. Even better, even if I had a long polynomial, let's say g of x equals 18x to the 5th plus 20x to the 4th plus 7x to the 3rd minus 2x plus 4. Well, this is going to go relatively quickly now. Remember, and we can treat every single one of these terms as a power. So we can say, look, this is really 5 times 18, that's 90, x to the 4th, plus 4 times 20, that's 80, x to the 3rd, plus 21, x to the 2nd, minus 2, okay, x to the 0th, which is, well, this is just 2. So this is 90x to the 4th plus 80x to the 3rd plus 21x squared minus 2. That's what g prime of x is equal to now. Okay, and this is a great little, more than just a shortcut. What we did here was a proof, and we know that this works for all powers when n is an integer. N is an integer. It turns out it works for non-integers as well, but we didn't prove that here today. Okay. And we can apply this just very rapidly. Let's review here and look back from what we did before. F of x equals ax squared plus bx plus c. Okay. Well, one of the nice things about the rule that we just proved here, well, in this case, we still got a times the power here, that's 2, times x minus the power, that's 1, plus b times the power, which is 1, times x to the 0th, which is just 1. This is f prime of x. So this is 2ax plus b. And there you have it. Well, this is probably your first truly difficult calculus proof for those of you who are new in calculus and will be taking calculus in the future. Thank you for watching. Have a wonderful day.